Good. So we were talking about generally about the hardness of the problems. This hardness included several classes. We talk about NP, P space L is the one that the space was logarithmic essential, and R co-NP, lots of other classes. Here we are going first to the NP-complete problem. This is somehow the style of the book as well. We talk about the NP, which is like somehow the main set of problems. Almost any practical problem is in NP. Very few that are not in NP. By NP, I mean NP-complete, actually. We will talk about them. Then we go above, then we talk about below NP and above NP, like maybe those problems which are harder than NP and those problems which are easier than NP. That's a style that we have it in the book, and we were talking the same thing here in the class as well. Good. Now, here for NP, we have for NP complete problem, we have two important problems. One is the three-partition problem. So one is three partition. The other problem, which is very important, is three set. So these are the probably two most important problems in NP. That if again, this is by assumption. We talked about the three set before, and I mentioned that actually Stephen Cook proved that SAT is NP complete. NP is easy, the complete part is hard. He showed that actually how we can represent a Turing machine using SAT problems. For any, like, what is a Turing machine? Turing machine is just some tape that there is some essentially cursor on it, or some writers on it, or a pen on it, and it can just read this one, write it there, or go left, right, and this is like essentially memory. You can think about the memory that you can write any things, and you can just move this pen anywhere that you want, but one at a time. So that's a Turing machine. He could show that this Turing machine can be represented with a SAT instance, and this SAT in some sense can simulate a Turing machine. You can represent. That's the way that he showed that SAT is a NP-complete problem, because it belonged to NP. Again, belonging to NP was easy to show that if somebody gives you a certificate in particular solution, we should be able to solve say whether this is a certificate or not, whether this is a solution or not. So that's for that part. Now, we talk about the three SAT versus SAT, and we show that actually SAT and three SAT are equivalent, or there is a reduction from SAT to a reduction from SAT to three SAT. Good. So and we talked essentially about the thing that three SAT is a hard problem. We will talk more about three SAT later. Now, here we want to talk about three partition and several problems that can be used for this one. This is a very important problem to get the hardness results, especially when we have numbers. Good. So here, in this class first, we are starting with the two partition. So what is a two partition? So this is the definition of two partition. Given integers a1 to an, you want to partition A into two sets, a1 union a2, and it is a partition, such that a1 and a2, the sum of the numbers are equal. That is called two partition. So three partition is a bit, maybe this is actually, so maybe it is called, this one, this is called also partition, but they call it also two partition. So two partition and three partition have maybe they're not the best names, at least one of them. In the three partition, we don't want to partition into three sets. we want to partition. So given integers a1 to an, we want to partition A into n over 3 sets. So we want to partition it into n over 3 sets, not to 3 sets. That's very important. But I will say why 3 comes. Such that each of these sets have equal sum. So in some sense, this 3 partition comes from this n over 3. But here, this 2 partition comes from this A1 and A2. Good. Now, this is the thing. So these are these numbers that are given to me, and you want to just make sure that I have. Good. Yes. So here the 3 partition, this number A1 and A2 to an is given, and you want to partition it into n over 3. Now, why you say n over 3? So this actually, the 3 can come better than n over 3. So we can assume further that all the AIs are between t over 4 and t over 2. But what was t? T is the sum of this. So we want to have n over 3 partition, and each of them should be, the sum should be t. So we can assume that each of these numbers are between t over 4 and t over 2. Now, this results in this fact that each AI contains exactly 3 items. That's actually the 3. So in some sense, this is the main reason for this 3 partition. Each set has only 3 items. Why this assumption implies this? The assumption that each AI is between 3 over 4 and 3 over 2. And actually, this is parentheses. It means that greater than t over 2 and less than t over 2. Any ideas? Now I can ask you. So it was, I had this, some of these tricks actually I learned from undergrads. And one of them was this, that when you ask question, you can say that if you don't, answer, then I start asking question, and I will say a specific person. So as someone who wants to answer why, if the numbers are between t over 4 and t over 2, then we have 3 in each. Yeah.
So if you do 4 of them, you know that they are at least t over 4, and the sum will be greater than t.
Exactly. So yeah.
For t over 2. Exactly.
So the idea is that why it would be exactly 3 items, because you can just assume that if there are, what would be the lower one? 3. So if we have 4 items, each of them is at least greater than t over 4. So the sum would be greater than t. The same thing also if there are 2 items, each of them is less than t over 2. So 2 items would be at less than t. So the only way is that each of them have 3 items. So that's the thing that actually makes the 3 partition very interesting, that these numbers, you want to make it such that each of them have exactly 3 numbers in it, each of these sets. Good. Yes. Yeah. So that's one assumption. So each of these sets have exactly 3 items. More than that, we can assume that each of these AI are very close to t over 3. But not only they are, we can make sure that these are just some t over 3 plus some noise. Why? We can just improve a huge number n to the 100 times the max of A. Max of A means that maximum elements time. maximum element of A. So this we need it as well to make sure that, I mean, because it might be the case that element of A or some of them are larger than n to the 100. So like something like n to the 100 times max of A to each AI. If you add it, these are like would be huge. So in some sense, these big guys, like if you can see it here. So currently we are talking with these guys, but what do? We are adding like some very big things to each of them. This would be very small things here. The same thing here, but so this guy is like that. This other guy like that. But this other guy is like that. So this is this max things that we are adding to each of these guys. Good. And we know that this, because there are exactly, so this is very important because we know exactly there are 3 of them in each state. We can afford to do that. If some of them were 2, some of them were 3, then we couldn't. That's the important one. And as I mentioned, 3 partition plus 3 sets, these are probably the most important problem to prove NP-hardness. Lots of problems are coming from one of these, especially if you have the numbers, 3 partition actually helps. You will see something that even without the numbers, actually that 3 partition can help. Good, any question? Fine, any? Question? Comment? Good. Okay. So not so fast. Good. So there are so for the number problems, so there is 2 partition and 3 partition. What is the difference between them? This is one thing that needs to actually beg some details. So when you want to prove NP-hardness when we have some numbers as the input, there are 2 problems. One is partition. The other one is 3 partition. But what's the difference between 2 partition and 3 partition? 2 partition wants to do it in 2 sets. 3 partition wants to do it in n over 3 sets. Each of them has size 3. This comes to the concept of weakly NP-hard versus strongly NP-hard. So in the like a weakly NP-hard, so NP-hard generally it is equivalent to weakly NP-hard. However, if it is just like NP-hard and it is only weakly NP-hard, often we can use some like problem, like algorithm like dynamic programming to solve it actually for or any practical problems. So the problem becomes harder if it is actually a strong NP-hard. So in the weakly NP-hard, we are allowed the numbers to have a value exponential in n. And the encoding length of these guys would be 2 to the n to the c, a log of that, which would be n to the c, which is still polynomial. So that's the concept of so in the weakly NP-hard case, we can these numbers can have exponential numbers, but we know that the log of them is still polynomial. And so these are the input problems. So in some sense, the problems are harder because you are allowing to have, I mean, very unrestricted input. In the strong NP-hard, we are considering essentially we are proving the NP-hardness when restricted to numbers which value polynomial in n. So when we, this is this concept of weakly versus strong NP-hard. The weakly NP-hard, we say that the problem is hard even when this happens, essentially. Even when I don't say even when, actually. We show that the problems are hard when these numbers are very large. In that case, the problem is hard. In the strongly NP-hard, we say that no, the problem, even the numbers that you are giving to me are small. Sometimes, even if they are if they are polynomial in n, the value of them. Note that if the number is exponential, still we can represent it with polynomial number of bits. So the number of bits should be, the input should be polynomial. That we always have it. And we have it in both cases. But in one, we are assuming that the numbers, it can be exponential and their log of them is polynomial. In the other one, we say that no, the numbers are so polynomial. And of course, if we can show that this problem is a strongly NP-hard, even when the values are polynomial, then it would be harder things. And so that's the difference between these. This also happens in approximation algorithm. A typical case that like the input. So this is the assumption that when we talk about problems, you can say that, okay, we are assuming the numbers that are given are polynomial in n. That's the way that maybe you want to start soon. Like this is the first attack for the problem. Because generally this problem would be easier. If the numbers can be exponential in n, sometimes begs more detailed techniques. There are several techniques. So this happens in approximation algorithms or other places. For example, I just give you some ideas. When the numbers are very big, note that we cannot, count through this one because it is big. So in some sense, we can somehow mention that if there is one exponent, so if there is one number which is like exponential, then in this case, maybe the weights which are much less than that, like exponentially less than that, are not that important. Because anyhow, this would be the dominant term for them. So in that case, so we can say that we can divide this weights into log n classes, and each of them is a power of 2. So if it is like in this case, actually, if the numbers are exponential, it would be n classes. And we say that if this weight, so we can say that if in optimum solution we have a particular weight, then these numbers which are much less than that, they are not relevant. You can just ignore these numbers and just focus on that one. That's a technique, a general technique that sometimes works, not all the time. So sometimes getting this result for the case that these numbers are exponential actually is non-trivial, quite non-trivial. But in general, you can think about that the numbers are polynomial. Good. So that's about this one. So we have this concept of weakly NP-hard and the strongly NP-hard. We say that in the weakly NP-hard, these problems are hard when the numbers are big. In the strongly NP-hard, we say that, oh, their numbers even are not that big, or even if they are polynomial in n, still the problem can be solved in polynomial time. It cannot be, it is, the problem is NP-hard. Good. Now, we have also, let me just clear everything. Good. So, in addition of this concept, we have weakly NP-hard and the strongly NP-hard. So, we have the corresponding algorithmic notion. That's the one that I mentioned. So, we have a pseudo-polynomial time algorithms. These are the problems which are polynomial in n. N is always the input, number of vertices in the graph, number of items, everything. And the largest number. Good. So we have two types of coding. We have the unary coding. Unary means that if you want to write number n, just put n ones. That's called unary. You have only one digit to represent the numbers. So you have only digit 1. So if you want to say, I don't know, number 200, just put it 200 ones. That's a unary. In the binary, of course, we have 0, 1, then we have, and generally, if you represent in binary, the number of bits the number of size of the bits that you need is log of the size of the numbers. In unary, you need exactly n bits for that. So when we talk about a pseudo-polynomial time algorithm, means that these are polynomial in n and the largest number, which is in the unary encoding we talk about. Then when we talk about the weakly polynomial, so weakly polynomials are essentially polynomials. So when we talk about the polynomial, we generally means weakly polynomial. We mean that, so the idea is that it is polynomial in n and log of the largest numbers. So in some sense, they should be polynomial in n when the numbers are represented in binary version. And finally, we have this concept of a strongly polynomial. That is harder, so we don't see too many of them, which are polynomial in n. So just the numbers, in some sense, that it is independent of how big are these numbers. And that's the one, but we see less of this kind of strongly polynomial. You can search more for that, for which problem exists. But generally, we have this kind of pseudo-polynomial, that pseudo-polynomial generally comes from dynamic programming. So when we have the dynamic programming, generally one dimensions or 2 dimensions might be based on the maximum number that you have. And that's the thing that we get pseudo-polynomial time algorithm. Otherwise, if the thing that we get it is just somehow independent of these numbers, then we get polynomial or strong. And the issue with the problem is as I mentioned, with the weakly NP-hard is that if you prove some problem is weakly NP-hard, it still leaves the option that maybe a pseudo-polynomial time algorithm exists. And pseudo-polynomial time algorithms are generally good algorithms in practice, because they say that if the numbers are small, we can solve the problem. And generally, you might also be able to, if the numbers are, you can say in the actual problem, the numbers are not big, or the dimensions are not big in practical problems. So we can actually solve the problem in polynomial time. So if we prove something is weakly NP-hard, is still not satisfying, because it says that maybe then you should try to find some dynamic programming for the problem. But if we say that the problem is strongly NP-hard, then we are essentially assured that there is no practical algorithm for the problem. Good. Now, having said that, now let's see what are the classes do we have here. Good. So here we have these things that, assuming that P is not equal to NP, so assuming P not equal to NP, we have this essentially things. So here we have this type of, we have a strongly polynomial time algorithms, then we have weakly polynomial time algorithms. If so the weakly polynomial time algorithm and weakly NP-hard are somehow near to each other. And then we have the pseudo-polynomial time algorithm. Pseudo-polynomial time algorithm can solve some problem which are weakly NP-hard. That's the idea that I mentioned. So if a problem is NP-hard, we can still solve it in pseudo-polynomial time. Pseudo means essentially almost polynomial time. And then if we cannot even solve it in pseudo-polynomial time, then we have a strongly NP-hard difficulty. It means that from there, I mean, we cannot solve anything, essentially. No interesting algorithm essentially exists for a problem if the problem is strong. And now, the difference between 2-partition and 3-partition is exactly this. So if you show that some problem, so you can actually start problem, maybe think about 2-partition. But if you show that the problem is somehow harder than 2-partition, means that it can solve the 2-partition, then the issue is that it only shows that the problem is weakly NP-hard. It means that there might be some dynamic programming that you can solve. However, when we show that actually the problem is strongly, like if we are showing that this problem is harder than 3-partition, because tree partition is strongly NP-hard, it shows that my problem does not have any dynamic. That's the idea difference between two partition and three partition. So let's see some example here. Good. So consider this problem. This is actually the first problem that the people considered it. This is the famous book of Gary and Johnson. So this they have this paper actually. It is in SciComp means Science Journal on Computing. That's important. Like three important journals essentially in computer science, like early ones especially. This is Journal of ACM, SciComp, Science Journal on Computing, ACM Transaction on Algorithms, Algorithmic, Science Journal on Discrete Math. These are like the five probably oldest journals in theoretical, not theoretical computer science. Journal of the ACM actually is more general, it's for all areas. SciComp is as well, but this becomes more specific when you talk about algorithmic ACM transaction on algorithms or Science Journal on Discrete Math. Good. So SciComp means that one, but they have this famous book, Gary and Johnson, Computers and Interactability, a Guide to Theory of NP-Hardness. That's the thing that we essentially built. That was the, I think it was 80 or something like this, or 79, that they had this book. It's a very famous book. It got lots of citations. And our book actually is the next version of that. And David Johnson, unfortunately, he passed away several years ago, maybe around 5-6 years ago. And he was actually my boss when I was at AT&T. So he was a very nice person as well. Great. Good. Now, they introduced this problem. So this concept of partition and tripartition came from this, that you are given n jobs with processing time A1 to AN, and you are given P processors. Each of them are sequential and identical. You want to assign these jobs to the processors such that you minimize the maximum completion time. This is generally called maximum completion time. It is called make span. So these are the type of problem called a scheduling problem. In the scheduling problem, you want to, you have some sort of jobs. They have lots of different conditions. This is the simplest one. Sometimes they have a start date, they have a due date. You need to do it in between. The lengths of them are important. Here, just mainly the lengths of them or processing time, which is important. We don't have the start date, due date, etc. And here you want to assign this job to processor to maximize maximum completion time. And maximum completion time is called make span. So, just let me give you an example. So you have these processors, and then these are the jobs that you have it. So each of them have a different length, maybe some this, and then you maybe want to give this one here, and then maybe this to a smaller guy, you want to put it here, and so on and so forth. When you have this is the P1, this is the P2, and so on. Is the problem clear? So if you want to get a reduction from, why is it easy to get a reduction from partition? Can somebody mention the ideas? We want to say a reduction from partition to this problem. But we want to say that we want to somehow we can reduce the partition to this problem. It means that this problem is harder than partition. Why? Harder than two partition. Here by partition mean two partition.
So if we have n jobs, and let's say that we have two processors.
Yeah.
It seems like if we can find a way to distribute them evenly, so the time completion will be less.
would be what?
Would be less. I mean,
so what was partition? Partition is that we want to partition this one into two sets such that the sum is equal.
Yeah.
So that's what the partition problem. So we want to say that how can we, what do we want to do? We want to solve the partition problem using the OR problem. That's the meaning of the reduction from partition to this problem. It means that partition can be changed the input. We will see these are the typical reduction that we are seeing. So we can change the input of the partition such that if we have a procedure that can solve this multiprocessor scheduling, we can get the input of partition, change it, give it to this one, find the solution, and then from this solution we give the output for two partition. So how can we do that?
And we should check that.
Talk a bit louder.
If we have two processors, then we should check that each processor consumes exactly some total time divided by 2.
Okay, so it means that, so we need to say what are the inputs. So the input of the partitions are just A1 to AN, correct?
Yeah.
So we will give the same job so that this procedure needs to have processing time. We will give the same A1 to AN. Now, this problem, what does it do? It just solves like, and how many processors we want to give it to this procedure who solves this multi-processor scheduling? Two processors. So the input would be, so we are giving this A1 to AN, and P is equal to 2. We will give this one to this problem. Now, we are saying that then we don't do anything. We say that solve the problem for us. It solved for us, and then it gives us some, it tries to say there is a procedure who minimize the maximum completion time, which is the minimizing the make span. Good. So it says that, okay, your make span is, I can schedule it such that the schedule would be this length, I don't know, length L. Then what do we do after that?
Then we should check that L is equal to total time divided by 2.
Exactly. So then we should just check whether this L is equal to sum of these AIs over 2. So that decides whether this problem, so you can consider the decision problem, yes or no problem. So for example, here, this problem, I mean, if we give it, we want to see whether there is a 2 partition or not, then we just give it this. And if L, the make span of this one, this is the best that these guys could do that. If it becomes exactly sum of AI over 2, then we are done. And what's the exact meaning? That if it is AI over 2, it means that there is no slack in between. There is no gap. It needs to fully, because that's the minimum that you need it. That's very important. Sum of the AI over 2 is the minimum that you needed. So if there is the solution of this size, it means that it should have exactly partition this size. There is no gap to base. Good. Now, okay. So then from this one we get weekly NP-hard problems, and it is important actually. This problem. Why do we say that? So the 2 partition, what is the problem is the 2 partition. The 2 partition actually has a dynamic programming. How can we solve the 2 partition problem? Using any dynamic problem?
With a 2-dimensional dynamic programming, one dimension is the number of used jobs, and the other is total time difference in now.
Yes. So you can actually, I mean, what is the 2 partition? So 2 partition actually is a special case of subset sum. So, two partition is a special in case of a subset sum. What is subset sum? Subset sum, you are given a1 to an and an integer, I mean k. The question is that is there a subset of? So this is the set that is given to you. So, is there a subset? With some with sum equal to k. So this is, as you see, that's a special case of the two partition. Why? Because the sum becomes to sum of the numbers over 2. That would be the case of for two partitions. So in the subset sum, this number can be anything. And this general problem, actually, we can solve it by dynamic programming, because Ali mentioned you can have a two-dimensional dynamic programming. One is that like the numbers that you have it so far, and the other one is that what is the sum of the numbers that you have it. And so this is a very easy dynamic programming. You can just think about it. That's a good exercise actually, and you can see it also on the web. But this is a very good exercise. And the interesting thing is that one dimension of this would be the sum of these numbers. So if these numbers are exponential, then this dynamic programming has exponential time. So this is the problem for the two partition, that it is not strong enough, or it is weakly NP-hard. If the numbers become very large, then the problem comes. So, and this is important from the practical aspects. Why? Because somebody, you will go and say, okay, I can solve this problem. This problem is like as hard as two partition. But it means that, okay, two partition would be hard, maybe non-practical case, that these numbers are exponentially large. But what about if these numbers are small? In that case, we can actually solve this problem in polynomial time. So, for example, this scheduling problem, which is a very practical problem. This is almost any factory or anything, they need such kind of things if you have the processing. All these computers are using these ideas. All this cloud computing are just using these ideas, this partition. So if you say that, oh, this only it is hard when it is, the numbers are exponential, let's say maybe that's not that much practical. Can you do maybe can you do the dynamic programming? However, here this is the case that we say that there is a reduction from 3 partition to this problem. If you if you show that, it means that even if these numbers a1, a2, or an are polynomial in n, still the problem is hard to solve. Now, how can we say that this problem is like? How can we give a reduction from 3 partition to this problem? Any answer? That's easy.
It's the same.
It's exactly the same problem. So sometimes I try to give, sometimes might be easier, but I just want that you understand exactly why it's easy. So of course, the solution here is written is p equal to n over 3. Just exactly the same approach that we have done it. However, the number of processors here would be n over 3. So, and that was this problem actually, this 3 partition was introduced by Gary and Johnson. And this problem, multiprocessor scheduling, was actually the motivation for them to introduce this 3 partition.
Can you say the definition of the partition problem?
Yeah. So let me just fill everything. So that's a good thing is that I can just go there. That is the technology. Otherwise, I've erased that one, so you didn't need to write it again. But this is a three partition. That these numbers are given to you n over 3 sets, and you want to divide this one into n over 3 sets. And as I mentioned, this is very important that we can further assume that each AI contains exactly 3 items, not anything at most 3 items. Because in general, if you say n over 3 sets, it might be the case. Some sets have only 1 item and one set has n over 3 items. But here it says no, each set also has only 3 items in it. And also you can assume that these AIs are very close to T over 3. Like essentially, yeah, T is the sum of the one for each set. And then T over 3, we can assume that these numbers are almost equal. A little bit noise only they have. Is it clear?
So is this a problem that is equivalent to or harder than the main problem, or
what do you mean by main problem?
That part that you say each set AI contains exactly 3 items.
Yeah, so you can say that even when it is the case, the problem is strong, is NP-hard. Yes, I mean, there is some reduction. This is like 3 sat versus sat. We could give a reduction from sat to 3 sat. So the same thing, it means that 3 sat is actually the hard equivalent of 3 sat. The same thing you can say for this problem. So these extra conditions are very important. When we, this is important things also. When we talk about algorithm, we want to find a general algorithm that can solve, I mean, all like in the most general form. We don't want to restrict it, so we can solve only for the problems that has this form. So that's the thing that I mentioned, even for, it would be good if you have an algorithm that can solve when the numbers can be exponential in n. Still they have NP. So in that sense, we like such kind of algorithm. When we talk about the lower bound, it is exactly the reverse. We want the lower bounds or hardness, which are for special cases of the problem. So we don't want to say that this general problem you cannot solve. We say that this general problem, if you consider it, even if you say that the number of items are like 3 per partition, even if you say that these numbers are very close to this average, even in this case, I cannot solve them. So that's exactly somehow the difference between algorithmic view and the hardness view. Algorithm want to solve as general as possible. Hardness want to be as specific as possible. Why? Because if you have that one, then you can use these instances to prove hardness for other problems. That would be much easier, as we will see it here. So like the fact that we know that there are only 3 numbers per set is important. Or the fact that these numbers actually almost are equal, except maybe a little bit noise, these are important to show some particular problems are hard. Yes?
So the assumption that we have that AIs are between T/4 and T/2 in the first place can also be removed because of this observation that we can add like a large number, even though they like.
Yes,
we don't have that.
Exactly. Yes, you can get that one. So you can add a large number and you can get this assumption as well. So this assumption that we had AIs between T/4 and T/2, I mean, that you can actually get it because we can add a very large number. If you add a very large numbers, then somehow you are forced to put 3 items per things. Because if you put it 4, it would be just too big for this one. Because the dominant term would be that big term. So that's a very nice view that, I mean, this is like, we try to get, as I mentioned, at the end, it becomes like this, that the AIs are just small guys and these huge guys are the one that determines the number in each test. That's actually the way that you can prove it, that AIs should be between these. These are like not hard problems, hard ways. These are the ways that you can work. Clear? Any question? Good. Okay. So let me. So, and as I mentioned here, so this problem from the third tree partition, you just put p equal to n over 3. So the number of processors would be large. So in some sense, now when the number of processors becomes large, if the number of processors actually is small, then you can solve it by dynamic programming. So in that sense, it exactly gives you the idea. Because this is two partition, then you can solve it. If there are 3 sets, also you can solve it with dynamic programming, actually. Yeah.
How do we force the processors to take exactly 3 jobs?
No. You see, so in the reduction, I don't need to show that this processor are doing that. So a 3 partition does not necessarily have this. So I mentioned that the 3 partition is hard even in that case. But 3 partition, general thing, the numbers are given to you. So you don't need to enforce that there are 3 per each processor. However, you can say that the problem, these multiprocessors, when these guys, the P's are, the jobs have almost similar processing time, also that even in that case is hard. Then you will use the specific instance of 3 partition in which all the AIs are similar. So in some sense, that's like when you prove that this problem is hard, even in this special case, it is at your discretion, or it is at your disposal, in a sense that if you want, you can use that things if it helps you. If not, you can just use the general problems. Good. Any question? Clear? Okay. So let's go for the great. Good. So now let's, work a little bit with this 3 partition. So this problem that we want to talk about is the rectangle packing. What is the rectangle packing? You are given n rectangles. A, this is a set of rectangles A, and a target in rectangle B. Can you pack this rectangle into this bigger rectangle? So, and you're allowed to rotate and translate to fit, but without overlap. So this is a very practical problem, actually. So you are given these guys, and the question is that, can you pack them into this bigger triangle? So this is the set. So this is the set A. And this is the target rectangle B. Clear?
We assume that the lengths are integer?
Yes, the lengths are integer. So let's, say, so you see, this is a problem that we came to this one from 3 partitions, some theory problem. We discussed about this number, the setup, we came to this problem. This problem turns hugely important. Why? Any idea that why this problem is hugely important in practice? So we may talk about P not equal to NP as a like $1 million problem. Maybe, I don't know, thanks to this inflation that we have it here, maybe 1 million is not that much anymore. But this problem, I will say this problem is $1 trillion problem. Believe it or not.
Maybe it's used for manufacturing, to store the things.
Yeah, manufacturing, I mean, that's, yeah, but it's maybe not they are not that wealthy manufacturers. There are some other companies that are very wealthy thanks to this. Think about any applications.
Shipping and very.
You are thinking about all the stuff. Think about e-commerce. And again, please go and see some of these YouTube videos that you will see that we will talk about actually this problem soon, I think this month as well, more general things. But what is this problem, which is $1 trillion problem? Any ideas? In e-commerce.
So, do you want to e-commerce?
Yeah.
I have some idea that they want to put some stuff on a truck.
As I mentioned, that's old style. Shipping, yes, that might be the case, but I want a much closer problem to this problem.
Is the problem exactly the same that they want exact vacuum or?
No, you want to say that these A guys, these rectangles that are given to you, whether you can put it in one target rectangle. I can give you some hint. Think about this, a target rectangle is the screen.
I think there's web advertising.
Web advertisement, that's $1 trillion thing. So just think about Google. I mean, now the stock went a bit down, but Google, Microsoft, Facebook, Amazon, all of them, they are making, this is exactly the problem that they are thinking. Think about these guys. So this is, this B is just a rectangle that you have it. This is the screen. I mean, it can be, not necessarily the whole screen, it can be a smaller thing. That's an advertisement, essentially, a space. You have it, advertisement banner, or sometimes they call it widget or something like this. And then these guys are just, these are the creatives. These are called ad creatives. Ad creatives are just generally just some images, essentially. And this problem that you want to put in this space, and these are the, I mean, predetermined that what are the size of that, because according to that, you will get paid. So these are the different size you want to put it there. And just think about it. If you can solve this problem a little bit more, so this is like, I think the Google alone, I think the last quarter, they got it something like, if I remember, the revenue was around 70 billion per quarter. Like per year, it's like 280 billion per year. And this is just Google, let alone Facebook and Amazon and others. Now the top guys are Google, Google, Facebook, Amazon, and then Microsoft. These are the top guys for advertisement. These guys, if they can pack one more, like if they can, instead of 9, they can pack one more. Like, I mean, 10% more money. 10% more money of it, I mean, $1 trillion would be 100 billion. So this is like a hugely practical problem, that how you can put it such that you can put all of them, essentially, this screen or this target screen that a user can see.
But couldn't we use some brute force or backtrack algorithms to use them? least practical?
Yes, I mean, that is the case. So it depends to the number of these. In that case, they can do some kind of backtracking and do that. But I mean, potentially this number can be larger. I mean, it can be a smaller things. And even, I mean, the running time, and one other important thing as well, the running time is super important. Why? This is the case also for this one. When you see an ad, all of this can be done in less than 20 milliseconds. You should decide which ads you want to show to a user in less than 20 milliseconds. So yes, if the number is smaller, you might do better things. But still, if you have polynomial time algorithm, generally there are simpler algorithms for this problem. And this if you want to do this essentially, this kind of backtracking or something, it might be this 20 milliseconds. You may violate it. Note that there are several other steps. Huge things happen when you see an ad. Again, I will probably discuss that one in one of these e-commerce in the YouTube. You will see this is a very complicated thing. I didn't know actually that one before going. This one especially, I mean, like Amazon and Google, that I went there and understood it. It's very complicated. Lots of things happening. It's like a factory things is happening. And this is a small part of it, and this part cannot take that much time. So if we can do this one efficiently, that's important. Even for backtracking, this one can take some part of that 20 minutes. Good. But you see, that's interesting. So you will come to talk about some numbers stuff, and then you become the $1 trillion problem. That it is important to give efficient algorithms. And in general, I mean, the whole NP-Hardness versus non-NP-Hardness is that we give more efficient algorithm for algorithm. So for this important problem. So that's important. And so there's a special case which is called exact packing. In this case, we don't have any gaps essentially. It means that you should exactly fill in this. And I mean, it would be, I mean, the hardness result is stronger in this case. If we can mention that even for this, sometimes you can say that for the special case that there is no gap, there is no hardness, or we say that it is osmosis. So when we want to say that of course, the procedure like doing the rectangle packing, that problem, if in the special case that you can do exact packing, also should give the answer. So in some sense, exact packing is a special case of rectangle packing. And we will focus more on exact packing. Good. Now, we want to say that this problem is hard actually. We can, of course, as I mentioned, it's a good exercise to, when you want to solve the problem, it is numbers is given to you. Try first 2 partitions. See what does it happen with 2 partitions. Then this gives you a weekly NP-Hardness. Then if it works, then you try to get it by a 3 partition. So from partition or 2 partition, the problem is easy essentially. How can we do that? These A's are equal to A1, A2, A3. These are like the ones that are given to you. And this is the length of them, and the width of them is epsilon. Epsilon is much smaller. So then this is the set A, and what is the target P? The target P is just one rectangle that its width is 2 epsilon, which is much less than or equal to 1. And what is its length? The length is sum of these AIs over 2. Good. Then in this case, of course, I mean, these AI things, these are now, for now, we are assuming that AIs are integer, epsilon are some very small thing. We will resolve this issue. Here, I mean, why do we get this guys 2 epsilon much less than or equal to 1? Because we don't want to allow any rotations. So to avoid any rotations, we are just making this one essentially the width small, and then say that, okay, solve the problem. So the only way is actually to solve the 2 partitions. Good. So this is the first result that we get. Now, can we generalize this one actually from, then if you have this idea, then say, okay, this same idea should work for 3 partition as well. Because you just make the length of this n over 3 times epsilon. That should be less than much, this means much less than 1. And then this is the case. Now, so is it clear so far for three partition? Why this problem is hard? Okay, somebody said, okay, you got the idea. Now let's go for the practical. Here you are using, the widths are very small. Can you resolve this issue? This is actually the idea. So you can actually scale these guys such that all these dimensions are integral. How can we do that? You just multiply everything by n. N times ai. So then essentially the width of these guys would be 1, but the width is equal to 1, but the length is n times ai. Actually, you can even do it additive. You don't need to do multiplicative. That's also not, I mean, as long as this is, why do we need this big one? We can put it essentially like, say, n plus ai. Why? And so n max of a, and so max of n and max of ai's plus ai. That's the number that you can put. It's the same number that we turned it, all of them are equal. So I want to put it like something like this. Max of n and a. Like all elements in A, this max of n, maybe actually we'll put it n plus. And the max of a set means maximum element in a set. Good. You can put it this additive thing. The main issue is that you want to make sure that these guys, they cannot be rotated. That's the whole idea. That you want to make them big such that you cannot rotate. Good. So you can do this one. So A would be this, B would be n times t, t again, this number. And now this one, the width of this can be n over 3. And we can use the 3 partition. Good. Let me actually bring this one down. Is it clear so far? Any questions? Yeah.
Can you solve like actually finding the package just from the decision algorithm?
Yes, I mean, these are generally, I mean, easy. So this is also a question that they ask, I mean, how can we solve the, like the packing problem from the, so these are the decision problem versus like finding the solutions. Generally, the idea is this one. If you have the decision problem, you can solve the problem. I mean, that's always the case. You can think about for specific things, but generally, if you have the items, sometimes you will include this item, say what would be the solution. Sometimes you don't include this item and see what is the solution. From this, you can, so if you include, say, what was the idea? So here, that we can, whether we can, this case would be a bit more tricky, but generally the idea is that from the decision problem, you can decide whether this particular element should be in the set or it should be in which set. Because if I include it, then I know that how much the capacity of this set went down, etc. And you can decide whether this is the correct one or not. That would be a good actually exercise for this particular problem, because this is 2D, that makes it a bit harder. But if it was 1D, that was easier, because you can include one item, then you remove you decrease the capacity of this set and say that therefore the rest of the items and this remaining capacity, can we solve the problem or not? But this would be actually a good exercise, that if we have a decision problem to solve whether this can be packed or not, can we find the actual packing from that? So yeah, I think that would be a good exercise.
It definitely exists.
It should exist essentially, because both of them are NP-hard problem and should exist. So the only thing is that how can we do it efficiently? But that's a nice problem to think about. Any other problem? Yeah.
What about if we have negative AX?
Negative AX. Yeah, so the question is that, I mean, what about if we have negative AX? I mean, this problem is defined for positive. I don't know. You may define some negative version of it. I don't know what is the.
I mean, so the two partitions, more positive numbers, then still.
Okay, so you are talking about the partition problem. Yes, I think for the partition problem, that's actually, sorry. Yes, for partition problem, that would be a nice problem, actually. I mean, if you have the negatives, what can you do? I don't remember on top of my mind. It was sometime when you have the negative, yeah?
I didn't get the question.
So he want to say that what about if you have negative numbers? It's the partition problems.
I'm going to find a dynamic programming algorithm for this, or just you want to say that it is NP-Hardness. You want to say that it is NP-Hardness. Let's say generalization from.
Yeah, if you want to say that the problem is NP-Hard, yes, this is generalization. You have both positive and negative. Now the question is that what about if we have negative numbers and we want to see, like for example, for the subset sum, you can, I think for subset sum actually you can do it. So you can say that you have positive and negative numbers and you want to see whether I can create a particular sum out of them or not. That you can still solve it by dynamic programming because you know what is the maximum, what is the size of all negative, what are the size of all positive, and you can solve that problem. So in terms of solutions for two partitions, you can solve it. If I'm not mistaken, you can solve it actually by dynamic program. Yes?
Can't you just apply the same scaling trick by adding like a large number so all numbers become positive?
Yes. So that actually something, yeah.
The number of items in each partition.
Yes. I mean, for if you use three partition, you might be able to do that. I mean, if you want to say for three.
Yes, exactly.
Exactly partition, yeah. But yeah, so I think you need to be careful, as he mentioned. So this trick, if you want to do that, you need to, a number of them, it is important. If you want to use this somehow a scaling trick to solve for the negative case.
You can just replace the negative numbers with the positive version. It's like if you would put the negative number instead of A, you just put the positive number instead.
Yes, that's also, I mean, that is for two partition, but if we solve two partitions or partition using subset sum. So then the question is that how do you solve because we don't directly solve two partition. But these are good problems. I think these are like, that's actually a good problem that I need to think to answer them. Yeah. And we can think about them. Great. So let me see whether we have anything remaining here. Yes, here, I mean, yeah, that's the thing that I have mentioned. Essentially, the previous thing that I have mentioned, that you can add, you don't need to multiply. You can add n over 3 plus ai for them. And then if you, t plus n would be the additive for here and n over 3 here. So you don't need to actually add. And here it is assuming that n over 3 is larger than a. Otherwise, you need to have max of n over 3 plus max of a plus ai's. This is a trick that you can do it. So even if it's the additive case, actually, you can do that. We will talk later. This is another interesting thing. So somebody can say this additive, this advertisement problem, say, okay, but here you are using the very thin rectangle. What about if they are supposed to be squares, almost squares? Can you show that the problem even hard in that case? That actually we will discuss it and say, even in that case, the problem is hard. Then we are talking about squares or almost like rectangles, which are similar to squares, not very thin rectangles. That might be not that important in advertisement. You don't show these thin things. Great. So I think that's it for now. Any question? Yeah.
In this part, do we have any constraints on A lines? So are they smaller than n over 3?
Yes, as I mentioned. So yes, we are assuming that AI is less than n over 3. Otherwise, you need to add n over 3 plus max of a, all elements in a plus something. Yeah.
For this problem, you're going to be partitioning and position on 3 partitions. And the reason for being 3 partition is more useful, right? Because that shows that strongly.
Yes, exactly. So generally, if you can do it from 3 partition, you should do it from 3 partition. So you should show essentially reduction from 3 partition. First, but it's like essentially like for 2 partition, or partition is the one that, I mean, essentially warm up. You do first for the warm up, and then you will do the actual things for the other one. Yeah. But that's a good warm up essentially.
Here it seems like there's a small change from partition versus
yes, as you mentioned. So here in this case, actually, there's not much difference between partition and 3 partition. Not always the case. Sometimes you need to actually do a little more than that. Sure. I mean, there are some. I mean, like the 2 partition itself. 2 partition itself is a problem that you can get the weakly NP-hardness. You can, and of course, you can get it the hardness from 2 partition, but you cannot show the 2 partition is strongly NP-hard using 3 partition. So there are some problems like that. Of course, this is a trivial one, but you can't find similar.